Most of the math you use today wasn't written by a committee, it was written by one man. This is the story of Leonhard Euler, the genius who turned the chaos of numbers into the language of the modern world. Part 1: The Basel Prodigy and the Russian Invitation. The story of Leonhard Euler is not just the story of a mathematician, it is the story of the man who defined the very language of modern science. To understand Euler, we must first understand the world into which he was born. It was April 1707, in the city of Basel, Switzerland. At this time, the scientific revolution was in full swing, but the tools we take for granted today, the symbols, the functions, the very way we write an equation, were a chaotic mess. Basel was a hub of intellectual thought, dominated largely by the influence of the University of Basel. Euler was the son of Paul Euler, a pastor of the Reformed Church, and Marguerite Brucker. His father was a man of some mathematical leaning, having actually lived in the same house as the famous Jacob Bernoulli during his own student days. Paul Euler's plan for his son was simple: Leonhard was to study theology and become a pastor, following the family tradition. However, the spark of genius was impossible to suppress. Even as a child, Leonhard showed a memory that was nothing short of miraculous. He could recall entire books of poetry and complex calculation tables with zero effort. His father taught him the basics of mathematics, but it was the family's connection to the Bernoullis that changed the course of history. Johann Bernoulli, the younger brother of Jacob and then regarded as the world's foremost mathematician, noticed the boy's incredible aptitude. Johann was a difficult, often arrogant man, but he recognized in young Leonhard a talent that might one day surpass his own. He began giving the boy Saturday afternoon lessons, though lessons is perhaps a loose term. Bernoulli would give Euler difficult problems to solve on his own, and then they would discuss the difficulties together. This guided self-study was the perfect fuel for Euler's mind. By the age of 13, Euler enrolled at the University of Basel. While he did graduate with a Master of Philosophy at the age of 16, writing a thesis that compared the philosophies of Descartes and Newton, his heart remained in the world of numbers. He spent his nights devouring every mathematical text he could find. When he finally told his father that he didn't want to be a pastor, it was Johann Bernoulli who stepped in to convince Paul Euler that his son was destined to be a great mathematician. This was a pivotal moment. Had Bernoulli not intervened, the world might never have known the name Euler. In 1726, Euler completed his dissertation on the propagation of sound, titled De Sono. At just 19 years old, he entered the Paris Academy Prize competition. The problem that year was to find the optimal placement of masts on a ship. Euler, a young man from landlocked Switzerland who had never even seen an ocean-going vessel, won second place. He was beaten only by Pierre Bouguer, who is now known as the father of naval architecture. This was the first indication that Euler's mind could solve practical, physical problems just as easily as abstract numerical ones. However, Basel was too small for Euler's ambitions. There were no academic positions available. Meanwhile, in the East, a new light was rising. Peter the Great of Russia had founded the Imperial Russian Academy of Sciences in St. Petersburg, hoping to modernize his empire. After Peter died, his wife Catherine I continued the project. The academy was desperate for brilliant minds. Two of Johann Bernoulli's sons, Nicholas and Daniel, had already moved there. When Nicholas died of appendicitis shortly after arriving, Daniel requested that his friend Leonhard Euler be invited to fill the vacancy. Euler arrived in St. Petersburg in May 1727. He was originally appointed to the medical department, but he was quickly moved to the mathematics department. Life in Russia was not easy. The political climate was unstable, and the academy was often underfunded or viewed with suspicion by the Russian nobility. Euler navigated this by immersing himself in work. He didn't just do math, he served the Russian state. He worked on cartography, helping to map the vast Russian Empire. He worked on the theory of shipbuilding and navigation. He even studied the scales of music, trying to find a mathematical basis for harmony. It was during this first Russian period that Euler achieved one of his most famous early breakthroughs, the solution to the Basel problem. For nearly a century, mathematicians had tried to find the exact value of the sum of the reciprocals of the squares. The problem asks, what is the sum of 1 over 1 squared, plus 1 over 2 squared, plus 1 over 3 squared, and so on, to infinity? This is written as the sum from n equals 1 to infinity of 1 over n squared. Great minds like Leibniz and the Bernoullis had only been able to find approximations. In 1734, Euler shocked everyone by proving the exact sum was pi squared over 6. Let us look at how he did this, because it shows his unique, intuitive style. Euler began with the Taylor series expansion for the sign of x. He knew that the sign of x is written as x minus x cubed over 3 factorial, plus x to the power of 5 over 5 factorial, and so on. He then divided the entire equation by x to get a new function. He treated this infinite series as if it were a massive, infinite polynomial. Just as a normal polynomial can be factored by its roots, Euler factored this series using its roots, which occur at pi, negative pi, 2 pi, negative 2 pi, and so on. By comparing the coefficient of the x squared term in both the series and the factored version, he found the relationship that led to pi squared over 6. This was a bold move that some mathematicians at the time criticized as not being rigorous enough, but Euler was later able to prove it with absolute certainty. This discovery made him an overnight celebrity in the mathematical world. But life in Russia was becoming dangerous. After the death of Empress Anna, the political atmosphere became hostile to foreigners. Euler became famous for being quiet and reserved. When asked why he spoke so little, he replied, "I come from a country where, if you speak, you are hanged." Before we move on to his move to Berlin and his incredible work on notation, I have a quick request. If you are finding this journey into the life of Leonhard Euler fascinating, please take a moment to like the video and subscribe to our channel. Your support allows us to keep producing these deep dives into the history of science. One more anecdote from this period involves Euler's incredible work ethic. The St. Petersburg Academy was tasked with calculating some very complex astronomical tables. Other mathematicians estimated it would take months of work. Euler, fueled by a terrifying focus, finished the task in just 3 days. However, the intense mental strain, combined with a severe fever, resulted in a tragic loss. Euler lost the sight in his right eye. He was only 28 years old. Most would have been devastated, but Euler simply remarked that he would now have fewer distractions from his work. This stoicism would define his entire life. He viewed his mind as a tool that functioned independently of his physical body. In this period, he also began developing the notation that we use today. Before Euler, there was no standard way to write a function of x. He introduced the notation f of x. He also began using the letter a, b, and c to represent the sides of a triangle, and the capital letters a, b, and c for the opposite angles. If we are calculating the area of a triangle, we might use the formula area equals 1 over 2 times the base represented by a times the height. By standardizing these symbols, Euler allowed mathematicians from all over the world to communicate in a single, unified language. He also popularized the use of the Greek letter pi for the ratio of a circle's circumference to its diameter. While he didn't invent the symbol, his use of it in his massive textbooks ensured that it became the world standard. By 1740, Euler was looking for a way out of Russia. He had achieved everything he could in St. Petersburg, and the threat of political purges was constant. An invitation arrived from Frederick the Great, the King of Prussia. Frederick wanted to turn Berlin into the cultural and scientific capital of Europe, and he wanted Euler to lead his academy. Euler accepted, and in 1741, he packed his belongings and moved his family to Berlin. This would mark the beginning of another 25-year chapter of incredible productivity, where he would transition from a young prodigy to the undisputed king of European mathematics. Euler's departure from Russia was not a goodbye, but a see you later. He continued to send papers back to the St. Petersburg Academy and even continued to receive a salary from them for years. He was a man of loyalty, but his move to Berlin was a necessity for his safety and the future of his family. Little did he know that the Berlin years would bring both his greatest mathematical triumphs and some of his most difficult personal conflicts with a king who preferred poets to mathematicians. Part 2: The Berlin Academy and the Standardization of Mathematics. When Leonhard Euler arrived in Berlin in 1741, he entered a world that was fundamentally different from the rugged, often survivalist atmosphere of St. Petersburg. Frederick the Great, the King of Prussia, was a man who saw himself as a philosopher king. He wanted to surround himself with the greatest minds of the Enlightenment. However, Frederick's relationship with Euler was complicated from the start. Frederick preferred the witty, sharp-tongued French philosophers like Voltaire. Euler, by contrast, was a quiet, pious, and incredibly practical man. Frederick often mocked Euler, calling him a limited mathematician because Euler didn't care for the social games of the court. But despite this lack of royal favor, Euler's 25 years in Berlin were perhaps the most productive in the history of science. The primary task Euler faced in Berlin was the formalization of mathematical analysis. Before Euler, mathematics was a collection of loosely connected methods. Euler wanted to build a cohesive structure. He did this through his monumental textbooks, most notably the Introductio in Analysis Infinitorum. In this work, he redefined the function. He argued that mathematics should not be based on geometric shapes, but on the concept of a function, written as f of x. This shift was revolutionary. It moved math away from the visual and toward the symbolic. One of the most important constants Euler explored during this time was the number e. While Jacob Bernoulli had touched upon it while studying compound interest, it was Euler who recognized its true power in calculus. He defined E using the limit as n approaches infinity of the expression, in parentheses, 1 plus 1 over n to the power of n. He showed that this number, approximately 2.71828, is the unique base for which the derivative of the function e to the power of x is actually the function itself. In spoken math, the derivative with respect to x of e to the power of x equals e to the power of x. This property makes e the natural choice for logarithms and exponential growth. Euler's work on e didn't stop there. He used continued fractions to prove that e is an irrational number. He calculated its value to 23 decimal places entirely by hand. He also discovered the power series for e, stating that e to the power of x equals the sum from n equals 0 to infinity of x to the power of n over n factorial. This means e to the power of x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. This series is the foundation of Taylor expansions and allows us to calculate complex values using simple addition and multiplication. During the Berlin years, Euler also took on a role as a tutor for the Princess of Anhalt-Dessau, Frederick's niece. Since he couldn't meet her in person frequently, he wrote her over 200 letters explaining physics, philosophy, and logic. These were later published as Letters to a German Princess. It became a global bestseller, translated into multiple languages. In these letters, Euler explained why the sky is blue, how the human eye works, and the nature of gravity. He was a master of science communication long before the term existed. He argued passionately against the monad theory of Leibniz, preferring a more Newtonian view of the physical world. In these letters and his formal papers, he continued to refine notation. For example, when dealing with a constant coefficient in a differential equation, he would often use the letter a. If we have a differential equation like a times the second derivative of y with respect to t plus b times the first derivative of y with respect to t plus c times y equals 0, the value of a determines the mass or the inertia of the system. Euler was the first to show how these abstract symbols could represent physical reality. Euler's life in Berlin was also one of massive domestic responsibility. He purchased a farm in Charlottenburg to support his growing family. He had 13 children in total, though the child mortality rate of the 18th century was brutal, and only 5 survived to see their father's later years. Euler was famously able to work in the middle of a chaotic household. His students often noted that he could write a world-changing mathematical paper while holding a baby on one knee and responding to his older children's questions. He claimed that the noise didn't bother him because he did most of his writing in his head before he ever picked up a pen. Despite his productivity, Frederick the Great grew tired of Euler's lack of a flair. Frederick wanted the Berlin Academy to be a place of literary wit, and Euler was too busy calculating the orbits of planets. When the position of president of the Academy became available, Frederick passed over Euler and gave it to the French mathematician D'Alembert, who actually turned it down out of respect for Euler. This snub was the final straw. Euler began looking for a way to return to Russia, where the new empress, Catherine the Great, was offering him a hero's welcome. Euler's final years in Berlin were marked by a flurry of work on number theory. He became obsessed with Fermat's last theorem. While he couldn't prove the whole thing, he did prove it for the case where n equals 3. This involved complex calculations with imaginary numbers, which Euler helped define. He was the first to use the symbol I to represent the square root of -1. He showed that every complex number could be written in the form a plus b times I, where a is the real part and b is the imaginary part. By doing this, he opened up a whole new dimension of mathematics that would later become essential for electrical engineering and quantum mechanics. As he prepared to leave Berlin in 1766, he left behind a legacy that Frederick would only appreciate years later. Euler had turned the Berlin Academy into a powerhouse. He had solved the problem of the motion of the moon, which was the GPS problem of the 1800s. Sailors needed to know the moon's position to calculate their longitude, and Euler's tables were the most accurate in existence. He was a man who lived in the world of pure logic, but his feet were firmly planted on the ground of practical utility. Part 3: Topology, the Seven Bridges, and the Shapes of Reality. One of the most fascinating aspects of Leonhard Euler's genius was his ability to create entirely new branches of mathematics out of seemingly simple puzzles. This is best exemplified by the Seven Bridges of Königsberg. In the 1800s, Königsberg was a city in Prussia, modern-day Kaliningrad, situated on the Pregel River. The river surrounded two large islands, which were connected to each other and the mainland by 7 bridges. The citizens of the city spent their Sunday walks trying to figure out if they could cross every bridge exactly once and end up back where they started. Euler heard of this problem and realized it wasn't a problem of geometry in the traditional sense. It didn't matter how long the bridges were or how wide the river was. It only mattered how the land masses were connected. This was the birth of topology, often called rubber sheet geometry. Euler simplified the map of the city into a diagram of dots and lines. In modern terms, the land masses became vertices and the bridges became edges. He reasoned that if you enter a land mass by a bridge, you must leave it by another bridge. This means that every land mass, except for the start and the end, must have an even number of bridges connected to it. He counted the bridges for each part of Königsberg. One land mass had 5 bridges, and the other 3 each had 3 bridges. Since all 4 land masses had an odd degree, the walk was mathematically impossible. Euler's conclusion was elegant: for a path to exist that uses every edge exactly once, a graph must have either 0 or 2 vertices with an odd degree. This is now known as an Eulerian path. This wasn't just a parlor trick. This discovery laid the foundation for graph theory, which is the math behind everything from how Google Maps finds the fastest route to how social media networks connect friends. Whenever you use an app to find a ride or a delivery, you are using the logic Euler developed while thinking about a Sunday stroll in Prussia. Following this, Euler turned his attention to the properties of solid shapes, or polyhedra. He noticed a strange consistency across all convex polyhedra, shapes like cubes, pyramids, and dodecahedrons. He discovered that if you take the number of vertices, subtract the number of edges, and add the number of faces, the result is always 2. This is the famous Euler polyhedron formula. V minus E plus F equals 2. Let's test it with a cube. A cube has 8 vertices, 12 edges, and 6 faces. So, 8 minus 12 is -4, and -4 plus 6 equals 2. It works perfectly. What about a triangular pyramid? It has 4 vertices, 6 edges, and 4 faces. 4 minus 6 is -2, and -2 plus 4 equals 2. Euler proved that this Euler characteristic is an intrinsic property of the space itself. This was the first major step in understanding the shape of the universe. If you were to punch a hole through a shape, like a donut, the formula would change. For a torus, or donut shape, V minus E plus F equals 0. This differentiation is how modern physicists categorize different types of matter and space. If you are finding this journey into the life of Leonhard Euler fascinating, Please take a moment to like the video and subscribe to our channel. In his exploration of surfaces, Euler often had to define the dimensions of his shapes using variables. If we define the length of a side of a polygon as a, then the perimeter is simply the number of sides times a. Euler showed that these relationships hold true regardless of the scale. This universality is what made his work so enduring. He wasn't just solving one problem, he was discovering the rules of the game. Euler's work also extended into the world of optics and light. At the time, there was a massive debate: was light a particle, as Isaac Newton believed, or a wave? Euler was one of the few high-profile scientists to side with the wave theory. He argued that light was like sound, a vibration traveling through a medium. While his specific theory of the ether was later proven wrong, his mathematical treatment of wave propagation was essential for the eventual development of Maxwell's equations. He used his math to design better lenses for telescopes and microscopes, correcting for chromatic aberration by combining different types of glass. His ability to visualize these complex physical systems was even more impressive when you consider his failing eyesight. By the time he was deeply into these topological problems, his one good eye was already beginning to fail. He spent much of his time in a darkened room, practicing the art of mental calculation. He would visualize the vertices and edges in his mind, feeling the geometry that he could no longer clearly see. This period of his life was also marked by a great deal of public service. He helped the Prussian government with the design of a canal system and worked on the logistics of the state lottery to ensure it was fair and profitable. He was a mathematician who believed that math belonged in the streets, the factories, and the ships, not just in the ivory tower. Euler's curiosity was boundless. He even looked into the mathematics of knight's tours on a chessboard. A knight's tour is a sequence of moves of a knight on a chessboard such that the knight visits every square exactly once. Euler was the first to analyze this using a systematic approach, once again using the principles of graph theory. He found thousands of solutions, including reentrant tours where the knight ends up one move away from the starting square. To Euler, the chessboard was just another graph, and the knight was just a point moving through space. This work is still used today in the study of computer algorithms and memory management. As we conclude this look at his middle years, it's clear that Euler was more than just a calculator. He was a visionary who saw the hidden structures of the world. Whether it was the layout of a city or the faces of a crystal, Euler found the underlying harmony. But his greatest challenge was yet to come. A return to the frozen north, a total loss of sight, and a series of personal tragedies would test the limits of even his legendary mind. Part 4. The Blind Titan and the Most Beautiful Equation. In 1766, Euler left Berlin and returned to St. Petersburg. He was nearly 60 years old, and he was coming home to an empire that worshipped him. Catherine the Great provided him with a magnificent house and a high status in the academy. However, tragedy struck almost immediately. A failed operation on his remaining eye left him almost completely blind. Shortly after, a massive fire in St. Petersburg destroyed his house. Euler was saved from the flames by a loyal servant, but many of his manuscripts were lost. Then, his beloved wife of 40 years, Katharina Gesell, passed away. In the face of blindness, fire, and grief, most men would have surrendered. Euler did the opposite. He famously remarked, "I shall have fewer distractions." He spent the final 17 years of his life in total darkness, yet this was his most prolific period. He produced a paper every single week on average. How? He used his incredible memory and a team of dedicated assistants, including his sons. He would perform complex calculations in his head and then dictate the results. His mind had become a powerful computer. One of his assistants once noted that when two students disagreed on the result of a complex series summed to 17 terms, they asked Euler to settle it. Euler performed the entire sum in his head and found the error in the student's work. He could also remember the powers of all numbers from 1 to 100 up to the 6th power. It was during these final years that his work on complex analysis reached its peak. We must discuss Euler's identity, often called the God equation or the most beautiful theorem in mathematics. It is written as e to the power of I times pi plus 1 equals 0. To understand why this is so profound, we have to look at the ingredients. We have E, the base of natural growth. We have I, the imaginary unit. We have pi, the ratio of a circle. We have 1, the basis of counting, and 0, the concept of nothingness. Euler linked them all in one simple sentence. The derivation is a masterclass in substitution. Euler started with the series for e to the power of x. He then substituted the imaginary value I times x for x. By rearranging the resulting series, he found that e to the power of I times x is equal to the cosine of x plus I times the sine of x. This is known as Euler's formula. When you set x equal to pi, the cosine of pi is -1, and the sine of pi is 0. This leaves you with e to the power of I times pi equals -1. Adding 1 to both sides gives you the famous identity. This formula is the heart of signal processing. Every time you listen to a digital music file or use a cell phone, Euler's formula is at work, converting waves into data. It bridges the gap between circular motion and exponential growth. Euler also continued his work on fluid dynamics. He developed the Euler equations for the movement of fluids. These are a set of partial differential equations that describe the conservation of mass and momentum. In a simplified form, for an incompressible fluid, the equations show that the change in velocity over time is driven by the pressure gradient and external forces. He used the symbol A to represent the components of acceleration in these equations. For instance, the acceleration in the x direction could be written as A sub x. His work allowed for the first real understanding of how water flows through pipes and how air moves over a wing. He also solved the three-body problem as it related to the Earth, Moon, and Sun. Newton had already solved the two-body problem, but adding a third gravitational influence made the math infinitely more complex. Euler's lunar theory provided a method of approximation that allowed for incredibly precise navigation. He didn't just solve it for the sake of math, he solved it so that sailors wouldn't get lost at sea. The British Parliament even awarded his family a prize of £300 for his contribution to the problem of longitude. Euler's resilience was bolstered by his faith. He was a firm believer in the logic of the universe. To him, solving an equation was an act of worship. He famously had a debate at the Russian court with the atheist philosopher Denis Diderot. As the story goes, Euler walked up to Diderot and said, "Sir, a plus b to the power of n over n equals x, therefore God exists." Reply. Diderot, who supposedly knew no math, was embarrassed and left the court. While this story is likely an exaggeration, it captures Euler's reputation as a man who saw no conflict between his deep faith and his rigorous science. If you find Euler's resilience in the face of blindness inspiring, please hit the like button. Be sure to subscribe to see our final part on his lasting legacy. Even in his final years, Euler was thinking about the future. He wrote a massive 3-volume work on dioptrics, detailing how to build better telescopes. He wrote on the theory of the motion of rigid bodies, introducing the concept of the moment of inertia. He was the first to realize that any rotation of a rigid body can be described as a single rotation about a fixed axis. These are now called Euler angles, and they are used today to track the orientation of spacecraft and airplanes. His house in St. Petersburg became a sanctuary of thought. He was surrounded by his grandchildren, whom he loved dearly. He would spend his evenings drinking tea and discussing the latest scientific news with his colleagues. He was not a lonely, bitter man, he was the center of a vibrant intellectual community. His blindness had not closed his world, it had simply forced him to see it more clearly with his mind. Part 5, The Final Calculation and a Legacy Without End. Leonhard Euler's life came to an end on September 18, 1783. The day began like any other. He had spent the morning calculating the orbit of the newly discovered planet Uranus. He then had lunch with his family and worked on some calculations related to the rise of hot air balloons, which were the cutting-edge technology of the time. While having tea and playing with one of his grandchildren, he suffered a sudden brain hemorrhage. He let his pipe fall from his hand and uttered his last words, "I am dying." Within a few hours, the greatest calculator in history had ceased to calculate. The impact of his death was felt across the globe. The St. Petersburg Academy was so overwhelmed by his unpublished manuscripts that they continued to publish them for 47 years after his funeral. It is estimated that Euler wrote roughly 25% of all the mathematical, physical, and engineering literature published in the entire 18th century. The sheer volume of his work is so vast that the project to publish his Opera Omnia, or complete works, began in 1911 and is still ongoing today. It spans over 80 massive volumes. Why does Euler matter so much today? Because he is the bridge to the modern world. Every time you use a computer, you are using the logic of Euler. The binary system, the algorithms of search engines, and the encryption of your data all rely on his work in number theory and graph theory. His work on prime numbers and the Euler-totient function is the very thing that keeps your bank account secure. Let's look at one final contribution, the Euler-Mascheroni constant, denoted by the Greek letter gamma. This constant is the limiting difference between the harmonic series and the natural logarithm. It is approximately 0.57721. It appears in formulas throughout physics and number theory. It reminds us that there is a deep, hidden connection between discrete numbers, like 1, 2, and 3, and continuous curves. Euler spent his life finding these bridges. In the world of engineering, the Euler-Bernoulli beam theory is still taught to every civil and mechanical engineering student. It describes how beams deflect and carry loads. If you want to know if a bridge will collapse under the weight of a train, you use Euler's equations. The formula involves the Young's modulus E, the moment of inertia I, and the curvature of the beam. It is written as E times I times the fourth derivative of W, with respect to x equals q. In this context, if the load is represented by A, then the deflection is directly proportional to A. Euler's legacy is also found in our celestial neighborhood. There is a crater on the Moon named after him, and an asteroid, 2002 Euler. But perhaps the greatest tribute to him is the way we teach math. When a teacher writes pi on the board, or uses the letter I, or explains a function f of x, they are using Euler's voice. He is the most quoted mathematician in history. The great Pierre-Simon Laplace famously said to his students, "Read Euler. Read Euler, he is the master of us all." Euler was a man of immense humility. He never claimed to be a genius. He simply said that he worked hard and that anyone could do what he did if they applied themselves with the same focus. This, of course, was an understatement. He possessed a unique intuition for math. He could see the answer at the end of a long path of logic before he even took the first step. He treated math like an explorer treats a new continent. He wasn't inventing these rules, he was discovering them. His personal life remains an example of resilience. He survived the loss of his sight, the loss of his home, and the loss of his children, yet he never lost his curiosity. He remained a kind, generous man until his final breath. He was known for helping younger mathematicians, often giving them his own ideas so they could publish them and gain fame. He had no ego. He only cared about the progress of human knowledge. As we look back on the life of Leonhard Euler, we see a man who truly saw the world in high definition. He saw the patterns in the stars, the vibrations in a violin string, and the logic in a simple bridge. He showed us that the universe is not a collection of random events, but a masterpiece of mathematical design. We hope this deep dive into the life of the king of mathematics has inspired you. Euler's story is a reminder that even in the face of literal darkness, the human mind can illuminate the entire world. Thank you for watching this full documentary on Leonhard Euler. If you've made it this far, you are a true lover of history and math. Please like the video, subscribe to the channel, and share this video with a friend who might appreciate the genius of Euler. Your support helps us keep the history of science alive. Until next time, keep calculating.